um, I'm really delighted to be able to talk about quantum spin liquids. This is a new direction for my group. And I have been fascinated by this state of matter because of how it upset our standard paradigms. But before that, let me just share with you what I'm missing, because I am in Paris, in Saclay, only figuratively, and I'm missing the wonderful croissant and coffee I know I would have had. I haven't been to Paris in over a decade. And I don't know, can you see the Camille Claudel hands, which is one of my favorite in the Rodin Museum. So that's something we have to give up in this time of Zoom seminars. Okay, so please do feel free to ask questions by just unmuting yourself, or I don't know how, Anuradha, you want to do it with chat?
Absolutely, yeah. Anyone who wants to ask a question, please unmute yourself.
The reason is I'm not checking chats and so on, so I'll just rely on you to stop me.
Sure.
Okay, so broadly, what I will do is, this is my roadmap. I'm going to start with the big picture because I assume not everyone is working on this topic. So I want you to see the importance of this area. And then I want to go into a very specific paradigmatic model, like the Ising model for phase transitions. The Kitaev model is a paradigmatic model for quantum spin liquids. And within that, I want to tell you about a recent discovery we have made using simulations. Already the Kitaev model is a model of spin liquids, but we discover yet another spin liquid when we apply a magnetic field. And so that's the part I want to tell you about in some detail. And you will see that in the Kitaev model, the interactions are very strange. Not anything like we have seen before in Heisenberg models and so on. And it's rather remarkable that such bond-dependent interactions can be engineered in real materials. So I just want to give you a flavor of what are the key ingredients in these materials. And then, of course, the key question of how do you detect a spin liquid? And this is a big discussion, and we'll only be able to touch on it. But this is something, with people doing NMR in the group joining in today, this could be really a good point of discussion later going forward. Okay, so the big picture. By the way, do you see anything covering up my slide, like the faces?
No, it's fine.
Okay, because somehow it's happening on my slide. Okay, so now let's say you are doing experiments. What would be the first signature of a quantum spin liquid? So I've sort of organized energy scales from UV. That's we are looking at a strongly correlated system. So charge physics is the really high energy scale. And essentially, we are going to be looking at Mott insulators, so that UV physics is on the scale of the charge gap. And we won't be concerned with that. Then you come to a middle scale, shown here in green, and this is where the local moments are revealed and local moments start interacting. So that would be the energy scale on the order of the exchange coupling J. Which goes like, some bandwidth square over U. So that's an intermediate scale. So we do have local moments, they interact. But now the main question that we always are interested in quantum matter is to ask about really the infrared or the low energy scales and ask what kind of emergent physics do we get there? And this is what we have been doing over the decades. And now we will see that with very similar looking Hamiltonians, some new kinds of low energy physics is emerging. So this just shows very basic measurements that are first done. And those are like the spin susceptibility, that can be obtained from NMR night shift as a function of temperature. And from the high temperature behavior, you can plot 1 over chi as a function of temperature and extract this Curie constant, which gives you an idea about the green scale that I just talked about. What is the nearest neighbor interaction between the moments? And so that is one important scale to detect theta Curie wise. And then you can keep lowering the temperature and see if the system orders. If it does order, and there is a singularity in the susceptibility, you can read off another scale, TC. So this ratio, theta Curie wise over TC, is the frustration parameter. And this is what we want to focus on to first start seeing signatures of a spin liquid. So in a spin liquid, this ratio will become basically infinity. That would be ideal because TC tends to 0. There is no ordering in a spin liquid, and F will now, in that case, tend to 0. But even if it has not totally gone to 0, TC, if F is large, it's already an indication that we have to pay attention to such a material. So I've just kind of put down the main requirements. You want a Mott insulator, which basically says an odd number of electrons in the unit cell. You want local moments that are small, either S equal to half, or if you have spin orbit coupling, then J effective equal to half. The moments are strongly interacting, so theta Curie wise is about a few hundred Kelvin in number of materials, and there's no magnetic ordering. And people have observed these frustration parameters to go down, to go up to as much as 10 to the 4. So we have such candidate materials. Now you may ask at this point, okay, so you've basically obtained a quantum paramagnet. And why would a paramagnet be interesting? This is, a question my program manager asked me, because he was like, so you're not trying to make a better magnet? And it came to him as a shock that I was trying to actually send TC to 0. So yes, that's something we must convince ourselves that, it is a quantum paramagnet, but what could be interesting about it? Now, what it actually does is it brings in a whole different paradigm in how we understand quantum matter. There is the usual Landau paradigm of spontaneously broken symmetry, which is described by a local order parameter. It adds to that a topological paradigm. And even within the topological paradigm, you can think of 2 avenues. One is what I call the integer quantum Hall effect. This is topology through Berry phases in the bands, but you can still understand it within a non-interacting picture with Berry phases. And this is where you can talk about topological insulators, topological superconductors, even Dirac point touchings, so you can have topological semi-metals. You can have insulators, but the band structure of the magnons, so you still have well-defined magnetic excitations, but the band structure of these magnons can have Berry phases. So all of this still goes in the category of what I call integer quantum Hall effect topological matter. But more interestingly and more bizarre is the fractional quantum Hall effect analog of topological matter. These are like the fractional quantum Hall effect and quantum spin liquids. These possess topological order. So it's a new kind of order. And the way it shows up is in the ground state having degeneracy on when you look at the ground state on different manifolds, cylinder, torus, and so on, it has a very definite ground state degeneracy. This is a bit difficult to experimentally measure, but theoretically you can look at it. It also has long-range massive entanglement, which I will describe later. And perhaps the most experimentally feasible signature is that the excitations are fractionalized. And all of these three things follow from what we call, or basically define topological order. X.G. Wen was put together these ideas many years back, and we are starting to understand it more and more deeply. And paradigmatic models play a big role in getting to these characteristics. Okay, and now the reason the community even more broadly is interested in these quantum spin liquid phases is because they allow us to not just make qubits for quantum information, but topological qubits, which are non-local and therefore robust against decoherence. I won't say much about that, but that is a big drive for the community. So before I get into my talk, it might be useful to just have a picture of what a spin liquid looks like. So if I take two spins, rather than organizing themselves into a product state, they form a spin singlet at the most elementary level, which is an entangled state. And these entangled states could just organize as a solid and break translational invariance. This we would not call a spin liquid, because as we see, the word liquid means it should not break any symmetries. And that's what you see here. This is a picture of a resonating valence bond spin liquid. What I should actually be doing is adding many such configurations with all possible pairings. And that coherent superposition really forms a picture of a spin liquid. Okay, so that's the picture to carry in your minds. It's a set of these overlapping configurations with specific phase factors that the system resonates among all of these, and that's what we would call a spin liquid. And the question is, what are the excitations of such a spin liquid? Let's contrast that with excitations that we know very well for an ordered magnet. Here, if you have a spin half magnet and you flip the spin, you create a spin 1 excitation. And these are bosonic magnon excitations that have well-defined energy and momentum. On the other hand, in this kind of a spin liquid, the excitations are formed by breaking one of these singlet bonds, and it produces these two up and down spins, which then can get deconfined. And in that case, such a state with deconfined spin half spin-ons has a very different character with fermionic excitations as its low-lying excitations. Now you might ask, why would a bunch of interacting spins ultimately not order at 0 temperature? We have removed all the thermal entropy. And it ultimately comes down to quantum fluctuations that arise from the Heisenberg uncertainty principle. And these are enhanced once you have low spin, low dimensionality, and frustration effects coming either from geometry or from interactions. And these are all the factors that ultimately lead to sort of a disordered liquid state. Let me just flash a few, since the characteristic that is most viable experimentally are the excitations that possibly fractionalized excitations. Let me just quickly flash the experiments in a one-dimensional system. This is a quasi one-dimensional copper channels, which are weakly coupled 1D channels. And these copper channels essentially have spin half Heisenberg, can be viewed as spin half Heisenberg magnets. And the ground state of such a system is indeed an RVB spin liquid. Now, rather than having magnons, because of the two spin-ons that are created, at a given momentum, you can share energy in multiple ways between the two fractions, or at a given energy, you can create spin-ons in multiple combinations of momenta. So you end up getting this broad spectrum. And that is really the signature of fractionalization. And this is inelastic neutron scattering data, which basically you can see such a system has some weak inter-channel coupling or inter-tube coupling, and that leads to ordering at 10 Kelvin. But even if you look at temperatures much above that, you continue to see this very large continuum in the spectrum, which is indicative that you have spin liquid physics extending way above zero temperature. Okay, so that was a quick background about the subject. At least you have a picture of a spin liquid. You see that it leads to these broad continuum of spectra. You might ask, are there some sharp signatures? And I'll come to that toward the end, because we don't want to just view the spin liquid as absence of many things, like absence of long-range order, absence of sharp excitations. We would like to see it as having some very definitive property. And I will come to that.
So can I just ask about that last remark, that you have ordering in fact at 10 Kelvin because of some lattice?
Because of inter-chain coupling.
Okay,
so once you get,
what happens?
Once you get this interchain coupling, then you get the quantum fluctuations are suppressed, and it leads to some long-range ordered state, 3D long-range ordered state, antiferromagnetic ordered.
Okay, but you're still able to, the bottom line is you can see this fractionalization signature nevertheless.
Right. So, so that ordering temperature is 10 Kelvin. So if you look above 10 Kelvin or energy scales above, 1 millivolt, 10 Kelvin is about 1 millivolt. So if you look at above 1 millivolt here, you see signatures of the spin liquid excitations. Okay. So let me come to now my next part, the Kitaev model. So this model is described on a honeycomb lattice, and at each site, you put a qubit, sigma. What is interesting about this model is that there is no geometric frustration. So it's not like a triangle which is geometrically frustrated or Kagome. It's a bipartite lattice. And yet the frustration comes from bond-dependent interactions. So you see it has three kinds of bonds, blue, green, and red. And on each of these bonds, a different component of the Pauli matrix interact between the two sites. So on the blue bonds, it's the sigma X interaction. Green bonds have the YY interaction, and ZZ interaction on the red bonds. So where is the frustration coming from? The frustration is coming from the fact that if you look at one of the spins, any of these spins, you can see it is getting three different signals from the three neighbors. One neighbor wants it to be aligned in the X direction, one wants it to be aligned in the Y direction, and the third one in the Z direction. And so this site is frustrated in not being able to decide on which way it should point. So that's the origin of the frustration in the Kitaev model. Now, what is remarkable about this model is that Kitaev was able to solve it exactly by making a parton construction. So parton construction basically is a statement that your spin operator is going to be fractionalized into two objects. And here he chose these two objects to be two Majorana fermions. And once you do that, any of these interactions now has four fermions sitting there. So you see one of the fermions, the B Majorana, they are both fermions, but one of them carries the bond index or a flavor. And this B fermion is localized. The C fermion is itinerant. So these B fermions on the different bonds, actually you can combine them around a plaquette to define a plaquette operator. And at face value, it looks like we took a two spin interaction and just wrote it as now a four fermion interaction. So that has not really simplified the problem, but he was able to see that these plaquette operators are in fact operators that commute with the Hamiltonian. So they can be considered constants of motion, and you can now analyze the Hamiltonian in different flux sectors. So these plaquette operators, ultimately you can go around a plaquette and define a flux that penetrates the plaquette. So the ground state of the system then looks like zero flux through all the plaquettes, and the C-Majorana fermions essentially moving on this honeycomb lattice, which is exactly the same as the graphene problem. And that gives you a Brillouin zone with K and K prime points that are gapless. So your excitation basically looks like gapless Majorana fermions with Dirac dispersion at the K and K prime points, and gapped flux excitation. So the first flux excitation you can form is to put a pi flux through one of the plaquettes, and this excitation is gapped. So you have a gapped flux excitation combined with gapless Majorana excitations. So this was Kitaev's major contribution. What we decided to do was to add a magnetic field and see what happens to it. And for purposes of my talk today, I'll just put the field along the direction that is perpendicular to the honeycomb lattice. What it does is it ends up opening a gap in the Majorana spectrum. And you might ask, what happens as the field is increased in strength? Now you might think that, I have a problem of spins which have formed this Majorana gapless structure at low energies. Let's look at the limit of an extremely large magnetic field. All the spins should essentially polarize along the direction of the field. And so we should just get a polarized state at large field. What we find is indeed that's the case. At very large field, you do find a polarized state with all the spins pointing along the direction of the magnetic field, but rather remarkably, in the middle, so let's look at this picture from the very beginning. At zero field, this is the Z2 Kitaev spin liquid. As the field is increased, a small gap opens up in the Majorana spectrum. At the same time, the flux gap starts to decrease. And at some point, the flux gap goes to zero, and that defines HC1. Okay, at that point, you have a lot of magnetic excitations or these gauge fluctuations in the ground state. But then we find that the system remains gapless for a whole range of magnetic fields, and only after that, another gap opens up and the system starts to go into this polarized phase. So this is one of our main results that I will now dig into, but I just thought I would show you this result first, just in case, so people can keep in mind our main results. The other thing we will also look at are the energies to create single excitations, single spin flip excitations, and two spin flip excitations. So once you're in the fully polarized phase, let's say the single spin excitation costs delta S. Typically to excite two spins, to flip two spins, costs double that, because these are two non-interacting modes that you're making at very high field. What we find is that these two energy scales behave quite anomalously in both low fields and also close to HC2. So that's another set of results I will show, because some of these excitations can be measured by Raman scattering. Okay. So let me point out some of the people who have done this work. David Ronquillo and Adu Wengel were the first ones to see that gapless intermediate phase through exact diagonalization. Nirav Patel then was able to describe the actual nature of that intermediate spin liquid phase. And I will show you that this spin liquid phase is quite different from the Kitaev spin liquid phase. it will turn out that it has a Fermi surface, which is quite unusual in an insulator. We don't expect to see Fermi surfaces in insulators. And Subhashri and Neerav Patel then did the work on the 1 and 2 spin flip excitations. I also want to acknowledge work from a number of other people on these topics. You know, here we are thinking we are asking this very unique question, but obviously there were many other people also asking similar questions. And I also suggest you look at their work, which has some overlapping aspects and some different aspects as well. Okay. So now I'll turn to our specific results, which are obtained by 2 methods, exact diagonalization and density matrix renormalization group. And what I'm showing here is the magnetization as a function of the field. And this is for let's just look at it. There's the magnetization as a function of field, and there are some signatures which can be highlighted. If we look at the susceptibility, then you see these 2 sharp singularities indicating the positions of these 2 HC1 and HC2. And you can also see that as we go to bigger systems, these 2 points move apart, showing that the gapless phase is not closing in on itself as the system gets bigger, but rather it's opening up. So that's a very clear evidence that we have 2 transitions here at HC1 and HC2. Now comes the next question: what is the nature of that intermediate phase? And for that, we look at the excitation spectrum. And what you see here, this is this axis here, the x-axis is field in units of the Kitaev constant. At 0 field, we had that Majorana gapless spectrum. And on a finite system, there is always going to be some small gaps. But nevertheless, what you see, so this already tells us that we have some estimate of the finite size gap in the system, the error due to a finite size. But nevertheless, what we see is that the spectrum is moving down very heavily. Huge density of states is building up in this intermediate regime. Okay, we can also look at the spin-spin correlations. And in the 2 phases flanking the central region, the spin correlations have an exponential power law. This is spin-spin correlation here. R is the distance between the 2 spins, and C of R is the correlator. So in these 2 regions flanking the center, the spin correlations go down as exponentially. But in the center here, this is a log-log plot showing that you get a straight line indicating that it's a power law with a power 1.5 that does not appear to change with field. So that's a clear indication that there are gapless excitations in the center. Okay, so far we have seen evidence for 2 transitions, and we have seen evidence that it's gapless. What is the evidence that it's a quantum spin liquid, you know, in terms of having this topological order? So here I turn to this concept of entanglement entropy. So if you take a system and break it up into 2 parts, A and B, and you trace out B, then you can get the density matrix of part A, and from that you can construct the entropy of A from trace rho log rho. And if it's a gapped system, so now I'm looking at not this new gapless phase, but I'm even before that in the Kitaev gapped. The point at H equal to 0 was a Majorana gapless, but when you added a small field, the system becomes gapped. That's the part I'm looking at. And if you have a gapped system, then there are only correlations at the boundaries. So typically SA scales like the boundary. So in this case, it's called the area law. but basically it's the boundary law. So the number of degrees of freedom in the system go like L square, that's a volume, but the entanglement entropy is only sensitive to this boundary, so it scales like the area law, linear with L. But if you have, so that's true for any gapped system, but if you have topological order, then there is a correction to that area law, and you have a reduction by this amount gamma, which is positive. And so getting a non-zero gamma is a clear signature that you have a topological order. And I'm not going to go into it, but there is a construction you can do thanks to Kitaev and Preskill by breaking up your system into parts such that the L part cancels out and you can read off just the topological entanglement entropy, which is this gamma value. So that's what we do in our systems. We break it up and we calculate this topological entanglement entropy. And I have put that along with the excitation spectrum we saw previously. And what you see is that there is a reduction below zero, which indicates that there's something topological entangled about the system. It reaches zero only in the fully polarized phase. Okay, now the analysis of that, this quantity gamma, let me just say one thing. A finite gamma indicates topological order, and it also indicates that there is a many-body entangled structure in the ground state wave function. It's related to the quantum dimension of excitations. I won't go into that too much, but these are some of the things that we can explore theoretically. So this is showing that even in a finite system, you have to be careful about how you make these partitions and extract gamma, but we do expect that gamma is equal to log 2 in the gapped phase, and we are able to get that in the gapped Kitaev spin liquid. Once we enter the gapless phase, it's no longer going to be given by this form. There are additional corrections that go like log L. So its interpretation is much harder, but the fact that it remains large and negative indicates that there is a topological order that we are still trying to understand in this gapless phase. But the fact that it is large and negative is already significant. Okay. Now let me turn to the spin-on Fermi surface. So coming now to that intermediate phase, we have to do large systems and take momentum cuts to understand where the low-lying excitations live. So we have these cuts in the Brillouin zone. And what is shown here is the structure factor S of K. So from the spin correlations, you can take the Fourier transform. And this is what would typically have been observed in neutron scattering. The point to remember here is the scale. It's a very small scale, just from 0.6 to 0.8. If this was true long-range order, you would have seen peaks of order size n coming from the long-range order in the system. Here, it's just a small variation, but it still shows where the low-lying excitations live. This is not the inelastic spectrum. We can also look at S of K at omega equal to 0. And we find that they indeed correlate with what we found in the total structure factor. So you can take these different cuts, you can see here, going from the gamma point to the K point and beyond, and you can see these variations which tell you that you have some reduction of weight here and enhancement of weight at these M points. So ultimately, we are able to suggest or infer. So we are not directly measuring a single spin-on. We are measuring the actual spin structure factor, but we can deduce the spin-on Fermi surface, these would be the spin-half fractionalized objects which form their own Fermi surface with a hole pocket at the gamma point and electron pockets at the M point. So this is a prediction that we can make that is still waiting to be tested in experiments. Maybe, how much time do I have, Anuradha, at this? You are muted. Sorry.
Okay, sorry. Yeah, about 15 minutes and then time for questions after that.
Okay, so maybe what I'll do is skip some of this 1 and 2 spin flips excitations, say a bit about materials just so we can leave more time for discussions. So among the materials, the main ingredients that we need for Kitaev materials. So as I said, spin liquids are not just confined to these honeycomb lattices. There are many lattices where you can see them, but specifically for Kitaev materials, the main ingredient you need is spin orbit coupling and Mott insulators. So you want a large U, which basically gives you a Mott insulator. And then you're looking at these transition metals, 4D and 5D. This transition metal is sitting in an octahedral cage, which splits the 5-fold degenerate d orbitals into a 3-fold degenerate T2G and a 2-fold degenerate EG. This crystal field splitting is very large, so we can ignore that. Furthermore, when you have spin orbit coupling, T2G combined with spin gives you 6 states, and these degenerate 6 states split into a 4-fold degenerate J equal to 3/2 and a 2-fold degenerate J equal to 1/2. Okay, now in the materials that we will look at, like ruthenium chloride, it has 5d electrons. So those 5 basically fill up the 4J3/2 state, and you're left with 1 electron in this doublet, or you can call it as 1 hole in this doublet. So it's very much like the cuprate problem, which had 1 hole in EG orbital. Here you have 1 hole in the J equal to 1/2 orbital. There's one big difference though. Because of this combination of orbital and spin, the wave function of the effective up and the effective down electrons in this J1/2 sector, they are made up of this dxy, dyz, and dzx orbitals along with spin. These wave functions are complex, and that will become important. And this is a difference from what happens in the EG sector, where the wave functions are real. So that's one ingredient. The second ingredient you need is these octahedra. When you look at 2 transition metal ions, you want them to be connecting with each other through an edge sharing octahedra rather than a corner sharing octahedra. And the reason for that is when it's corner sharing, there is a direct exchange between these 2 transition metal ions. And typically direct exchange between half-filled orbitals will lead to Heisenberg interactions, which are fully symmetric in spin space. On the other hand, if it's edge sharing, then you can see that there are 2 paths by which these transition metal ions can exchange, the electron can hop along 2 paths. One is along the upper ligand, chlorine or oxygen, whatever you have, and one is along the lower one. And there will be the complex nature of the wave function will lead to some interference between these 2 paths. And that is what will kill, for example, let's say if it's a Z bond, it will kill the X and Y interactions and leave only the Z interactions between the spins. So that's the basic idea. So I think I can skip that. I just want to acknowledge that Jacqueli and Khalilulin had this wonderful quantum chemistry idea showing how this interference was crucial to creating these bond-dependent interactions. Okay, so the very last part on how would you detect. So there are a number of experiments that can be done, and among them, inelastic neutron scattering has been done, specific heat and so on. I'm not mentioning all of that. I just want to go to one experiment, at least for the gapped spin liquid. It can provide a smoking gun signature. And to some extent, there has been success, though I think we need full confirmation still of that experiment. So let me set it up here. What you have is you apply, for example, so this is a thermal Hall conductivity measurement. So you apply a heat current along the x direction in a magnetic field that is perpendicular to the system. And you can measure, of course, you can measure the thermal gradient in the same direction as the heat current. That would give us kappa XX, the longitudinal thermal conductivity. You can also measure delta Y T. So the gradient of the temperature in the Y direction under the condition that there is no heat flow in the Y direction. And that would give you kappa XY. So that's what we would like to measure, kappa XY. And the reason for that is that when you have this gapped spin liquid phase, it gives a very particular prediction that kappa XY should be exactly half of the quantum of thermal Hall conductance or thermal conductance, which is pi square over 6 kb square over h bar. This half comes from the fact that we have Majoranas, which are essentially conducting the heat. So where is this Majorana coming from? We are talking about the gapped spin liquid. That's the gap in the bulk. There is a bulk boundary correspondence which leads to edge states on the boundary, very much like the charge fractional quantum Hall effect, which leads to edge states, these Luttinger edge states. And because this Majorana is half a fermion, that's the origin of that half. So that's what we are looking for. Now the material, alpha ruthenium chloride, is one of the candidate spin liquid materials. It has a Kitaev constant of about 80 Kelvin, but it also has some other interactions which are spoiling the perfectness of the Kitaev material, some other Heisenberg interactions, which ultimately at the lowest temperature gives rise to some ordered zigzag state, very much like that copper compound I talked about. So you want to get away from that. And one way to get away is, of course, to raise the temperature, but another way is to apply a field parallel to the plane. Remember what I said about the Hall effect, you want the field to be perpendicular. Now, this is a different component which is used to kill the ordered phase. So what you can do in the experiment, and what I'll show you the experiment in just a bit, is you apply the field at an angle. The parallel component kills the zigzag phase and gives you possibly a spin liquid phase and further on a polarized phase. And the perpendicular component generates the Hall effect conditions, the thermal Hall conditions. So in kappa XY as a function of T, one is expecting to see this plateau here with a value which is half of K quantum. Okay, so what object carries the heat? And it's essentially not the electron or the spin. The electrons are gapped out. It's not the spin or the phonons. It's really this Majorana edge mode. Now here's this really beautiful experiment from Matsuda's group. And what they measure is kappa XY as a function divided by T as a function of H perp. So with some H parallel that has been used to kill the zigzag order. And indeed you see this quantized value at intermediate field. So that's a very nice experiment, except people are still waiting for confirmation from other groups, and also confirmation on possibly other directions of the field, because there are some other predictions on that. But this kind of experiment would be like a smoking gun experiment, which directly sees the signature of the Majorana at the edge. So let me just conclude with these results. I'll just put them all up here. Basically, our predictions for Kitaev magnets. We are building on the model from Kitaev and the work of Jakeli Khalilulin. And this summarizes everything I have said. We start out at 0 field with the gapless Z2 spin liquid with Majorana modes at the K and K prime points. These become gapped in a small field at a field of HC1. This gap, basically the flux gap closes. This particular Majorana gap actually keeps increasing, but the flux gap closes. And then you get this gapless phase, which has Fermi surfaces at these M and gamma points. And beyond that, even at large field, I didn't get into that, but you can get these magnon bound states. And as signatures, we talked about the quantized kappa xy in the gapped phase. But furthermore, if this gapless phase, which is still to be observed, this would also have signatures in the thermal conductivity by showing the existence of a Fermi surface through low-lying specific heat, which would go like temperature, as well as kappa xx, which would scale with temperature. Okay, so let me just come to the very end. We are taking this work in many new directions. We want to understand prediction, come up with clear predictions for Raman scattering, predictions for spin and heat transport, and also then move toward doped spin liquids. Thank you.
Thank you, Nandini. On behalf of everyone, thank you for a lovely talk. You've left plenty of time for questions, so I think we'll wait for people to unmute their mics and ask some of their questions now.
So if I may,
please go ahead.
Yeah, I had a question. Two actually. Thank you very much for a nice talk.
You can turn on your video, maybe.
Yeah, I can do that. Yes, right. That's better. Just to be sure, what's happening at low field? So you start from a gapless state, and then you go to the gapped phase at low field. So how does it go? Is it should I think of the gapless state in 0 field as unstable, or is it a smooth transition, or how does it go?
Yeah, so the smallest field opens a gap. So it's, okay, it's unstable to even a small field. And that Majorana gap will keep increasing with field. But another gap, which was very high, like the energy to add a flux, which was a very large gap, will start decreasing with field.
Okay.
And ultimately, the flux gap will cross over. So if you are just looking for a gap in the system, you don't know what kind of mechanism is contributing to the gap. You'll see the gap go up and then non-monotonically come down.
Second question, if I can. And then above HE1, so there is this this spin liquid with a Fermi surface. So should I, if I would measure some standard heat capacity or susceptibility, should I find something like a metal, or
yes,
would that be the signature basically?
Yes. You should see very much like a metal, which is neutral. So if you measure specific heat, it should not matter whether it is neutral or charged, and you will see a linear specific heat. The power can be modified a bit It need not be just T, because these neutral spin-ons are swimming in a background of gauge fluctuations, which can modify that power. But nevertheless, it will go like T to some power. The thermal conductivity also will go like T. But of course, Wiedemann-Franz is totally violated because sigma is 0.
I understand you. Okay, thanks.
Yeah, I may have something related to that. You didn't, you said Wiedemann-Franz was violated. So in fact, in the ruthenium compound, are there interesting transport measurements as well? Or so is it just
so there are some very
what you expect?
Yeah, there are some very old transport measurements which showed that these were insulating or semiconducting, they called it at that time. But now it's known that these are Mott insulators. So people have measured that gap also through transport. It's not always reliable in transport because if you have disorder, that can obfuscate the actual gap. But I think there are also through ARPES, there is basically already in DFT, which is of course not a good guide for Mott insulators as we know, but you see very flat bands at the Fermi surface. And when you turn on interactions, these get gapped.
How about other questions?
So I've got another one if you want. Sorry. Now in many real material, there is a mixture of Heisenberg and Kitaev physics, and basically it seems you recover the Kitaev physics by applying a field, like that's the case in ruthenium chloride, for instance. So how does this, and then what you're explaining is that the Kitaev physics also evolved with the field. So how does it combine into real material? I mean, for experiments, so this interplay between Heisenberg, Kitaev, and the physics of Kitaev under field.
Right. So I think it's important to try to get materials where even if you can't get rid of the Heisenberg interaction, if it can be small. So in ruthenium trichloride, the Kitaev interaction is about 80 Kelvin and the Heisenberg interaction is about 8 Kelvin. So it's one order of magnitude smaller. So this separation of scales is a good start. And then basically once you apply a field, 1 Kelvin is about 1 Tesla for spin half systems. So once you apply a field of about 7 Tesla, you practically go into Kitaev physics. So that's one way. Another way that Kalulin has talked about is using cobalt, which is a 3D system. But he has shown that there is some very different routes to get, again, Kitaev physics in cobalt systems. And the interesting thing there is cobalt is a much smaller ion than iridium or ruthenium because those are 4D and 5D. So the direct exchange, Heisenberg exchange could be even smaller. So there are many people who are trying to simulate models with J, Heisenberg, Kitaev, Zhalushinsky, Maria, everything in it, and producing colorful phase diagrams. I have tended to stay away from that because I just feel that the Kitaev physics is really beautiful. And I just want to sort of extract that and keep trying to get rid of the other things. So certainly field is one way. Quantum chemistry by designing materials is another way. And if none of these are possible, even temperature may be a way. to go above any ordering temperature to see what are the, the indications of spin liquids will be there even at much higher temperatures.
Yeah, I wanted to ask a naive question about that. In most studies of frustrated magnetism, you run into this sign problem. So is that another reason to look at the Kitaev model? Maybe, or do you also have similar problems? Technically, are there any advantages to looking at this particular frustrated problem?
This problem also has the sign problem if you try to do quantum Monte Carlo. That's why we have actually gone into it very cautiously, first with just exact diagonalization, because it's a bit like doing a numerical experiment. We don't really have any intuition. Our intuition failed miserably because we were expecting a polarized phase and we got a gapless phase. So we know we didn't have the right intuition anyway. In such cases, it's really difficult to do theoretical analysis with approximations because you may well throw the baby out with the bathwater. So we started with exact diagonalization, then we expanded to bigger systems with density matrix renormalization group. Now we are slowly going into trying to get the shape and position of the Fermi surface using variational Monte Carlo. So this has similar problems of sign problem. So you have to ask very targeted questions that method can answer.
Another naive question. What is the magnitude of the gap? Is that just the Zeeman or is it normalized by some way by J?
Yeah, that scale starts out at J, at the Kitaev constant.
So it's not Zeeman itself.
No, it's not Zeeman.
Mm-hmm.
At the very high fields, it is Zeeman, but at the lower fields, it's not.
Okay, so it's
collective. It's more of a collective gap.
Any other questions? I think people are reflecting about your talk, Nandini. So, maybe we can stop and thank the speaker again. I'll do it. Thank you. And
thank you all for coming. And yeah, if you have questions later or if you have ideas for experiments and things to measure, I would be very happy to discuss more.
Good. Yeah, I think the magnetism community is actually pretty, in the Paris-Saclay campus. So between the neutron people and the NMR, that's a lot of folks. So good subject for all of us. Thanks again. Okay. Bye-bye, everybody. Thanks for coming. Bye.
Bye. Bye.